Now that we've learned about the basics of routing, flooding, shortest path, spanning trees, and so on, and we've also learned about the distance vector protocol, Bellman-Ford algorithm, the linked state protocol, or Dijkstra's shortest path first algorithm, in this video I'm going to put it all together and tell you about the structure of the internet, how hierarchical routing works, about interior and exterior routing protocols, and the breakdown of the internet into autonomous systems. I'm going to be talking about three main things. First of all, hierarchy and the decomposition of the internet into autonomous systems. The second is, within those autonomous systems, how we use the distance vector and linked state algorithms that we've already seen. And the third one is the resulting structure of the internet. Let me start with the hierarchy. When we learned about distance vector and linked state algorithms, we were considering the network to be a single collection of routers. This is really impractical. The internet's made up of millions of routers interconnecting over 1 billion different users. And so simply for reasons of scale, we need to decompose routing into smaller sets. So we do this for scale. With a large number of routers, the sheer scale of exchanging routing information between the routers and keeping it up to date makes it too hard. I mean, imagine exchanging the link state information with 1 million other routers. The network would just be flooded with updates all the time, and the distance vector algorithm would never converge. So that decomposition takes place into different autonomous systems, and there's examples shown here. This would be one autonomous system, and this autonomous system contains different routers. That's these. This particular one has one exit point, and we'll see the significance of that in a minute. And within that autonomous system, the system is free to pick its own interior routing protocol. In other words, to decide how packets are routed around within this autonomous system. So this particular type of autonomous system is called a single exit or a stub autonomous system. There's another type of autonomous system called a multi-exit or multi-exit autonomous system. For example, this one here. This is one where, in this particular case, there are 3 exit points. And again, it's an autonomous system, so they are free to determine the way in which packets are routed within that autonomous system using the interior routing protocol of their choice. This is because they're trying to, the internet was designed to give administrative autonomy. The internet was built up by many different entities, and so an entity over here might be Stanford's network, whereas this here might be, for example, a provider like AT&T, who is routing our packets to other networks. And because of the different entities that grew up over time, and there are tens of thousands of them, all with their own individual goals and desires. One of the original goals of the internet was to allow each organization to independently decide how it would run its own piece of the network, to allow it to organically grow. And in many ways, this was a big factor in the success of the organic growth of the internet, particularly during the 1990s, and allowed each one to decide what routing protocol it would use inside its network. So it means that, for example, at Stanford, we might use the interior routing protocol OSPF in order to route our packets, whereas inside AT&T they might use RIP, or they might use another one that's called ISIS. It leads to local customization. It leads to differentiation. So AT&T here might compete with Verizon here, and they can differentiate and provide a different service. Hopefully for me, the end customer, a better service as a result through competition amongst the operators. And by allowing for local customization, it means the vendors of the routers can also offer different types of features and functionality, and so it leads to competition amongst the router vendors as well. So for all these reasons, the internet was divided into autonomous systems. Autonomous systems, or ASs, are the basic unit of hierarchy in the internet. Within an AS, the owner decides how routing is done, and between ASs, we must use BGP4. This is the Border Gateway Protocol, and it's defined by Internet RFC 1771. And this allows for a consistent method for all of the different ASs to communicate. And we'll be learning about BGP4 in a later video. If you want to find an AS number, you can do this in a number of ways. One way to do it, actually the simplest, is to just do a trace route to a particular destination with the -A option, and this should give you the AS numbers of the ones in between. Most or many enterprises will have a single AS. For example, Stanford's, if you find it, will be 32. AT&T's is 797. Some enterprises choose to break down their own network into multiple autonomous systems. For example, Google has 3 that are reported, and some networks even have dozens. It's a slightly more complicated way of finding it, but specifically querying would be this way. And that is to query using netcat NC. If you perform this, so it's essentially going to this particular whois provider and then entering a particular IP address, it will tell you the autonomous system that that IP address belongs to. So if you wanted to find the AS number for Stanford, you would first do a DNS lookup for stanford.edu, find that in its A record this is the primary address. Then you can find the autonomous system for that particular IP address by doing this, by entering it here, and then that will return AS32. Let me show you a couple of examples of those right now. Let's say I wanted to find the AS number for Stanford. I could start by looking up the record for Stanford, and we can see it here, the primary A record address, and then I can do the lookup to the using netcat to the whois. This is just folks that provide a particular one that I like. If I put in the address here for Stanford, and then we'll see it returns the AS of 32 down here in the left-hand corner for Stanford. Similarly, if I wanted to find the AS numbers for the routers along and the networks along the path from my computer to, say, Netflix.com, I could use the traceroute minus A option, and here we go. Let's look at this here. So at the top we see, or near the top, we see the AS32 corresponding to Stanford. Down the bottom we see the AS2906 corresponding to Netflix. We'll see one here which is AS65534. This is basically saying that it's a private address, 10.33.0.2, because it begins with a 10 as a private IP address used inside Stanford. So given it's a private address, it's not able to return an AS number. And in the middle here we see 2152, which is of Scenic, which is the California network that connects us to between Stanford and some outside providers. Now we know the basic structure, let's look at the interior routing protocols. I've already mentioned RIP, or the Routing Information Protocol, and this was the first widely used interior routing protocol in the Internet. It uses distance vector, in particular the distributed Bellman-Ford algorithm. It's described by an Internet RFC. This is actually version 2 of RIP, which is the one most widely used. It sends updates every 30 seconds and will determine that a router has become unavailable if it hasn't heard within 180 seconds or 3 minutes. So there are no authentication for updates, meaning that there are definitely some security implications of using RIP. RIP became popular to start with because it was originally in the BSD version of Unix, and there was a daemon that was widely used, widely available for routers that were using RIP, and that was it's pronounced routd. And you can find many references to this on the web. So it was widely used for many years. It's used a little less now because of the convergence problems that people have found with RIP. And it tends to have been mostly replaced by OSPF or ISIS, which is very similar to OSPF. So OSPF is defined in Internet RFC 2328, and it's a link state algorithm. So link state updates are sent using flooding. And in case I didn't say this before, we use flooding because during the time that we're trying to find the topology of the network, we don't know how to reach anyone, so we don't have any topology information. That's why we're flooding the link state information. So we can't route the link state information to every router because we don't know the path. So flooding is the simplest routing table free way of making sure that every router in the network finds out the link state. So that's why flooding is used. It runs Dijkstra's algorithm, as we know. The updates are authenticated, meaning that we're sure that they belong to the router that we are communicating with. Because some autonomous systems are very big, it's quite common to partition them down into areas. So our own campus network here at Stanford is partitioned into OSPF areas. It's widely used, it's quite complex. This is a gross simplification here, but it gives us the basic ideas of how OSPF works. So once we know how to route packets within an autonomous system, it's worth asking the question of how do we route them from within an autonomous system to a different autonomous system? So how do they make it first out of the autonomous system? How does the interior routing protocol isn't going to tell us directly how we exit from an autonomous system because it's dealing with the addresses of routers that are outside of this autonomous system. So there are really two cases that we need to think about. One is when we're routing to a single exit point. So this would be from a stub autonomous system that actually only has one exit point. Much easier in this case than in the more general case where there are multiple exit points. So if there's only one exit point, routers within the autonomous system can use what's called default routing. Each router knows all of the prefixes within its autonomous system. So it knows all of the prefixes inside the autonomous system. And packets for another autonomous system are sent to what's called the default router. And the default router is the border gateway to the next autonomous system. So it's nice and simple. It essentially says, if you see an address in a packet that you don't know what to do with, then just forward it to the default router. And default routing means that the routing tables in the single exit ASs tend to be very small because each router only needs to hold the addresses for the prefixes within its autonomous system. Otherwise, it just forwards them out. Nice and easy. Life is more complicated when we need to route to multiple exit points. So this would be in a transit autonomous system or one where there are multiple exit points. This has actually become much more common in the last few years because nearly all sizable enterprises like Stanford will connect at multiple exit points to different providers. So we might connect to an educational backbone, a research and education network, and then we will connect to one or two commercial providers just in case one of them goes down, one of them is temporarily unavailable, one of them is perhaps too expensive for a particular route. It allows us to choose and have control. So multi-homing is very common. Now we need to choose for each outgoing packet which exit point it will take. So the problem here is that each internal router must be told which exit point to use for a given destination prefix. This is the essence of the problem. That means that when it sees a prefix which is not inside the autonomous system, it has to know which exit point to use. So this means it requires very large routing tables so that potentially routes to every prefix. And so the routing tables in a autonomous system with multiple exit points tend to be very, very big, tens or hundreds of thousands of prefix entries. This can actually be made a little simpler if the autonomous system uses what's called hot potato routing. Hot potato routing is when instead of making a smart choice in the best interest of the packet and its destination, it simply sends to the closest exit point. In other words, it says for any given router, it sends it to the exit point closest to it if it decides it's not for within the autonomous system. Hot potato routing is also seen as offloading, somewhat a selfish act by the autonomous system, because it's offloading the packets as quickly as it can to become somebody else's problem, and is not very popular with its neighboring autonomous systems. But it is actually very widely used today in the internet for both commercial reasons and reasons of simplicity. The more elaborate way would be to pick the exit which is closest to the destination or is on the lowest cost path to the eventual destination. And that requires the dissemination of more information within the autonomous system in order to make that decision. Now we've learned a little bit about how routing goes on within the autonomous system. I now want to explain a little bit about the exterior routing protocol, BGP4. Every autonomous system in the internet must interconnect to other autonomous systems using BGP4. Just like we're required to use IP in order to deliver our packets, that's what the internet uses. The thin waist of routing protocols is BGP4. In other words, it's the one that we must all use. So I'm going to describe BGP4 in a separate video, but I just wanted to tell you a little bit about the problems that BGP4 was designed to try and solve. First of all, it has a very different problem for an exterior routing protocol than for an interior routing protocol. Specifically, when we're considering the topology, the internet is a very complex mesh of different autonomous systems and has very little structure to it. You've seen the picture, which is the logo for this class, and will have seen that it's a very unstructured interconnection mesh. And so trying to exploit that, any structure, is not going to get us very far. Each of the autonomous systems is autonomously controlled. So they might define the link costs in very different ways. So it's not possible to find lowest cost paths. We're simply going to have to find a set of paths based on the number of autonomous systems that they pass through. Another thing that we need to consider is trust. When we're going between autonomous systems, we'll find that some autonomous systems aren't willing to trust others. Perhaps they don't trust them to advertise good routes, e.g. they might be a competitor, or they may want to protect the privacy of their traffic. So they might not want to send traffic through another autonomous system. For example, it might be a warring nation. Another reason that, or another thing that BGP4 was set out to solve was the question of independent policies. So different autonomous systems have different objectives. Some might try to route over the fewest hops. They may prefer one provider over another. They might have a lower cost arrangement with one provider compared to another. So they have local policies that they perhaps don't want to share with others. And in general, these policies are kept secret. And so BGP4 is designed to work in a way that will allow for that policy to be a local, private matter for the autonomous system. So we'll see BGP4 in more detail in a different video. Finally, I want to just tell you a little bit about the structure of the internet as we've seen it so far. So first, at the top level, there are what we would all recognize as internet service providers. They might be companies like AT&T. They might be, in Japan, it might be NTT. There's about a dozen of these what are so-called Tier 1 ISPs. And they are defined as ISPs that are fully mesh interconnected with each other and who peer each other without charging each other. It's called settlement-free peering. In other words, there's no money that goes across this interface between them. They then connect down to what are usually called regional ISPs, which might correspond to a state or a county or a region of a country. And those in turn connect to below them to what are called the access ISPs. So there would be many access ISPs along the bottom here. And these would be the ones that we connect to as users. So users are down below these access ISPs down here. And they will connect up here, and an access ISP might connect to multiple regional ISPs, and the regional ISPs will generally connect to multiple tier 1 ISPs. So this hierarchy is one in which there's a well-defined relationship between each of these entities. So in general, up above is the provider, and below is the customer. So the provider is providing service to the customer, and that goes on down all the way down. So in going down, this is the provider and this is the customer. And generally, the provider will charge the customer. So in other words, in order to send packets from the regional to the tier, then money is charged, a settlement charge. Generally, they keep track of all the data that's sent over there over some period, like a month, and then they will settle after that time. So there would be money charged in that direction. But there's no money going in this direction across here. So in order to save money, it's quite common for the regional ISPs to have connections across here so that the packets between access ISPs, if there's a lot of traffic, it can actually go through the regional ISP without going to the tier 1, and therefore they don't need to pay for that. So this is the basic internet infrastructure. Tier 1 ISPs, about a dozen of them around the world. And then regional ISPs, generally within a country or within the region of a country, and then access ISPs, which are the ones that we connect to in order to get access to the internet. So in summary, the internet consists of multiple autonomous systems, ASs. Each are managed independently. An AS runs its own interior routing protocol. In other words, it chooses the one that it will run. And in the case of stub ASs, they use simple default routing, and so they're very simple. ASs with multiple exit points must decide the best exit to use when routing packets to other autonomous systems. ASs must connect to each other using the BGP4 protocol, which we're going to learn about in a future video. That's the end of this video.